Great, thanks, everybody. That's great. So now we have a bit of time to have a discussion. I want to seed, we'll have people come up and ask questions. I want to seed the discussion sort of like yesterday, because this is the mirror of yesterday's missions panel. And ask the question, just like yesterday, we kind of, you all have your own dimension, right? I mean, the complementarity of these different simulations across the sun and earth and different physical regimes and so on was really manifest and very interesting. So what is the first thing you personally would want to do when you got your hands on punch data with your model? Maybe we start with Elena.
Okay. So once we see the first punch data, we're going to run the simulation, camera simulation, and I guess, synthesize the synthetic images and try to identify maybe similar features, or the model will give us something completely different and try to understand why. But I think my personal interest, I would like to understand, looking at punch images, I would like to understand what is the kind of interactions that they're showing us. And I think this is where models will come in and will help us really to understand the interaction of structures that we're seeing.
Mm-hmm.
This is a hard question I hadn't thought about much, so I'm going to just answer a different one. And I think we're related at least. But I think similar to what we were talking about yesterday, we've got a lot of different varieties of models, and mine being the weirdest of them. I think a lot of the comparisons are both very well observed about how we can do with punch. If Elena's simulation has all these details, you cannot get my model, and we run something similar to mine and see where they compare similarly and where the differences are. Having that higher resolution, we might be able to sort of identify other features and see what's missing in one versus the other. And I think there's a lot of cross-model comparison similar to the cross-satellite comparisons we had yesterday.
So I think for the first thing, I would definitely say to like really map and understand these really weird dynamics things going on in the time-dependent simulations that we see, and we're not so sure what it is, if it's physical artifacts or so. That's where I would look first. But if the first punch data also has a CMB in it, then I will be really very much interested to see its evolution also further than these 30 solar radius, because there are many studies that show the deceleration of the CMEs, for example, when observed at Mercury and Earth, and then we suggest a lot of ideas, but very curious to see where and like how it's along its propagation, its changes or deforms or decelerates or accelerates, of course, as well. But like that, I'm very, very curious and very looking forward to investigating actually.
I think the first thing we would need to do would be to validate the model, starting with the wind, that time accurate solar wind, particularly reproducing SIRs, make sure that we really have the basic physics right. Under those circumstances, start with solar minimum, working our way to solar maximum, and then of course with coronal mass ejections. The really interesting thing would be if we could match and relate to a whole host of observations that are complementary to punch, so we could look at everything that's observed in situ, or solar probes, or orbiter, type 2 radio bursts. If we could actually relate a physical process, something that's being observed across a wide range of scales, or a wide range of both in situ and remote observations, then we could really nail some things down very concretely the first time.
Great. And the thing is, there's a lot of things I want to do with punch data, and I'm sure more broadly, our group would have different answers to this question. I think similar what Chip was mentioning, I was asking stupid questions about background correction, because just validating the electron densities in our model, I think having PV from 6 solar radii at 45 degrees in the heliosphere could provide a lot of information and sort of validating observations about how bad are we doing with the density structures, things like that. Obviously, tracking coronal mass ejections, I think what Dave Barnes was showing in collaboration with Erica, just demonstrating that we can use this for tomography purposes and reconstruction, I think would be really interesting. And then obviously I showed the time-dependent moving on purpose because I think, especially with the model that starts at the surface, we could track, okay, here's a streamer disconnection block. How does that evolve in the heliosphere model, and then compare that to the
So I think the first thing that we would look at is look at the observations where there are no CMEs. Because we would like to see if our simulations can be compared to the first half decade of inertial range that the punch is supposed to be able to resolve. And if we can make a correspondence between those, we can do more work on trying to see the kind of thing that Francesco Pecker was doing last year, which is to try to see if the forward modeled observations are anything about the actual turbulence properties. Then, if we can solve that problem, which is not trivial, then if we can get the turbulence distribution throughout the heliosphere verified by punch, then we can start doing more accurate statistics of field line tracing back to the corona and stuff like that, and SEP transport coefficients, and maybe even drag coefficients for the CME modelers. So there's a lot to do, but punch is key in verifying it.
Yeah, Bill's gonna be busy.
What's that?
You're gonna be busy, Bill.
Francesco's.
Yeah, sure. And a reminder, everybody, try to keep your mic a little bit off to the side when you talk. Okay, go ahead.
Great. I was curious. To what extent for each of your models will we be comparing the punch structures, the mesoscale structures in a statistical way versus to what extent you think we can really do one-to-one comparisons? Like, for example, Cooper, do you think you can really get a blob that really would be similar to the kinds of streamer blobs, or are we needing to approach this more statistically? That's actually to everybody, but I call that you specifically.
Yeah, I think it's a nice first yes. Yeah, I think if you're really doing the time to aspects of the it's really going to be a statistical thing. It's very hard if you're driving with a full front half of the magnetic field to get CD to erupt at exactly the right time, exactly the right place. But you can complement that with dedicated case studies. Let's say there's a pristine punch observation of a streamer disconnection or a very nice CME, then you can build a model with trial and error with some of the tools we're trying to build to facilitate that case study. So I think both are possible, and it just kind of depends on the frequency and nature of events.
Yeah, we have a lot of work to do in terms of being able to reproduce a wide range of mesoscale structures. Our shown so far is a very extreme version. Extreme circumstances and then extremely strong magnetic fields, really extreme mesoscale structure. But I think what we need to look at is definitely circumstances where these structures form much more frequently on a larger scale with much weaker perturbations in general.
I totally agree with what was already mentioned, but when looking at the simulations, the time-dependent simulations that we've done, and that's limited for now, we could see that these dynamics also have very different types of dynamics that arise. And it's also like this density enhancements, and that's sometimes linked to the heliosphere current gene and so on, sometimes not. So it's also case dependent. So I think in that sense, doing this statistical, like this global approach will really help us understand what we're doing wrong, because we are probably doing something wrong, but because it's many different layers of that. So this availability to many of this data, I think will really help to constrain this.
Said before. I think for Gamera, since we don't have the ground component, we started beyond alpha zone, and with the high resolution simulations we resolve everywhere in the domain. I think it would make sense to do some statistical study on different structures that we see with the shock and sheath in the solar wind. But I also think it would be useful to look at maybe more simple cases of interactions. I mean, they're going to be idealized, but I think we can learn a lot. What do we expect to see if the scene interacts with the stream here or here? And I think it will give us some understanding of how this interaction looks like, and I think we can see some similar shapes and features in punch data.
Hi everyone. This is for Elena, but anybody can chime in. I know that this is the first and foremost point of what you're doing. So no is a complete sentence and a reasonable answer. But are there any tracer particles or Lagrangian markers in your magnetic field that help you identify exactly what magnetic field line you're looking at as it propagates? And the reason I'm asking is because there's a lot of fundamental physics that relies on us knowing exactly which field line, conceptual or not, we're dealing with, and how those smaller scale interactions can inform the larger scale structures that we're seeing later. So do you have any tracer particles or Lagrangian markers or anything that helps you identify your magnetic field lines?
This is an excellent question and very timely. So, yeah, we have started working on particle tracing in the web, and this is very at the very beginning now. So we will have this capability soon. So far, we've been just tracing magnetic field lines from any location, but it's not, it's not in the Lagrangian sense yet. This is definitely something that we're very, thank you.
I
Yeah.
wanted to, just a quick, so that capability is in the master, and I just can't underscore how useful that is.
Yeah.
For a variety of applications. Ron added this like a decade ago, basically. We use it for tracking, how portions of coronal mass ejections erupt differently and looking at, particle trajectories. So I think that could be really neat in a lot of different contexts that are relevant to punch. So we should figure out better ways to see that, so it's always there.
I'd like to make a comment. Which hopefully will not get lunch food thrown at me by my colleagues. Because Rohit Chipper in our group has done some studies looking at mapping field lines from the sun out to 1AU and the other way around, taking into account the observed levels of turbulence. And if you just do sort of standard Jacobi and Parker kind of field line random walk, or its more sophisticated descendants, any of them, there's sort of like a 15-degree cone of uncertainty.
Yeah.
And I personally think that the question that you asked is a great one, but I basically think it's in the end an ill-posed question because you can't do it. If you take into account the fact that there's fluctuations, if the field lines were laminar, sure, you can do that. So if you coarse grain them and make them laminar, you're gonna get like the mean field line. But if it's spread over 15 degrees, you have to rethink your conclusions, I think.
Right. I mean, I didn't say it was easy. It's tedious work.
It's going down the path of fundamental. And then this is to any and all of you, right? We know corona is a low beta plasma. And if you're doing kind of your modeling from the surface utilizing magnetic field data, that you will get the topology right, especially. And so, that's not the thing, right? You're getting the shape right, and now with high spatial and temporal resolution data, you can introduce evolution, dynamics, all that is great. But we still don't know what the source of the heat of the corona is. Some of you are saying you have that, which is fine. I mean, if we can use physics to do that, but where is the validation? So we do have data. Parker is flying in this region where we are not only seeing whisper data, we actually have in situ density, magnetic field velocity, and with a mission like PUNCH, you should be able to extract density with PV. But where is that validation? I'm looking for, models are going on, but what are we extracting? If I take the model and try to extract this information, will that be the same as what the corona is telling us if we did in situ? To me, this is still sort of the unresolved problem of what we can observe with remote sensing observations. But ultimately, what we want to infer are these physical parameters. And then we have a basis for how is the corona heated, accelerated, all of those. So probably you have answered this, but I'm still kind of trying to understand where is this going on in the equations. Thank you very much.
We're doing a lot of that, and I guess with the, we'll have to air some dirty laundry, just tell you how we'll see it. So one of the issues is the solar acceleration profile. As Marty mentioned, we're getting something different than 1 over r squared because the solar wind accelerates. We're finding that our model doesn't accelerate as quickly as it is observed, and that's been well established in our validation papers. NISTA has published 2 validation papers which are very, very extensive in comparison with observations, one for solar minimum, one for solar maximum. We can certainly greatly expand upon that with PUNCH data and trying to fit the density profiles. One of the other things we're looking at are spectral line observations to see about the heating, specifically below corona, and looking if it can reproduce the velocity profiles, especially the non-thermal velocity, right? Now, phase wave density is, should be associated with, obviously phase wave motions, thermal velocities. Can we reproduce both the thermal and non-thermal component of the solar as well as reproduce the temperatures? And one of the things we're finding is maybe we're not reaching the maximum temperatures in active regions, so there's probably some type of reconnection going on. Nanoflares, it's not part of our model that might be necessary to at least reproduce active region temperatures. But these data are definitely available, and we are working hopefully diligently to make comparisons and corrections.
Part is done a validation study with Parker Solar Probe data also. So we try to do multi-spacecraft, multi-viewpoint validation every time we are running our models. And as was said, there are of course caveats, but yes, but that's something that we diligently try to do.
Maybe one more point with regard to this. In sort of future presentations with the modeling stuff, it would be awesome to actually put your validation metric, what you have calculated, and what is the ground truth. Because in many cases, that's why we are flying these missions, providing observational ground truth. And I know that, maybe PV is the only way you get density, and everything else is a convolution of density, density squared, temperature, abundance, lots of things. So to kind of really make progress, it would be actually those products or just point out so that everyone can jump in and bring some of those observations. Just suggestion, thought.
Yeah, well, first off, I want to say it's really the multi-instrument remote sensing institute, spectral data, AIA, PV, white light, every single piece of data you can get your hand on is critical for this sort of model validation. For example, I had the experience where I optimized the EV model for AIA, and when I discovered our PV was too low, and I chose a different abundance, and I could bring those in. But the thing is, you can't over-optimize for any one observation, because then you can screw up other stuff. So you need a lot of different observations to go in. But a big challenge you have in modeling is, okay, I'm wrong. What do I do, right? And then if you try to fix your solar wind, you can mess up something else in your model. It's not easy, and one of the major issues is you don't necessarily know if it's the physics in your model or the boundary conditions in your model, like magnetic field observation. So I might have a structure 20 degrees off that is right, but looks wrong, right? And I think Yasmina pointed that out too, that if you look at the 2D slices, you can get a very different impression of which model is good and which model is bad by looking at the 3D content. So this is a very challenging problem. I want to do a simple metric and turn my model into one number that says good or bad, but it's not that easy, and that's a big challenge.
We wouldn't do it if it was easy, right? Maybe you can say we need more resources, but I'm trying to figure out, how do we bring everyone together, right, towards one common goal?
I'm gonna remind people, let's not talk too much except in the mics, because people online won't hear you.
Sorry.
Yeah. No, that's good. No, you can talk as much as you want. You have a mic.
I think there's growing evidence that energy is being input to the turbulence in the corona. Greg's famous green plot in his 2018 paper indicates that there's shear present. And the recent studies of failure of WKB theory approaching the alpha point suggests that there's significant energy input approaching alpha inside. So just putting waves in at the lower boundary probably isn't enough to get the profiles correct. And not only that, but in ESIS data, looking at the timing of that, at least one SEP event, we found that you had to include something like field line random walk to get the path lengths correct, because they were off by about 40%. So I think the turbulence effects in the middle corona and outwards toward Park areas look like they're in fact important.
I'm going to add a challenge. Pretty soon we will hit the declining phase of the super cycle, and it's time for the big storms. And the big storms usually occur when we have a succession of events, one after the other, like the May storm. So did you guys thought about simulating the storm like May or the one that will be probably coming in the fall? And how do you set up your models for that?
Yes. Yeah, obviously there are certain CVs that become a huge interest in the community for a variety, maybe they're really extreme or maybe they're very well observed. And obviously resources are limited if you're doing a very, very careful case study, but that's what we try to pick is the ones that people are very interested in. And then if it is a case study, you have a lot of time to sort of optimize what are my boundary conditions, what is the model that I'm using to energize the configuration, how do I erupt it? And this is where then having these pristine observations like what PUNCH provide is very useful then for model validation. I mean, maybe I can't argue that this is what happened, but I can produce a model that's consistent with what happened and learn from that. And yeah, obviously.
Looking to our previous work with the modeling the Hubble events, very extreme series of CV events. We published a series of papers in 2008 on that, exactly the same thing. There was a process of trying to produce solar wind. Now we have to be time dependent and then have to produce a series of eruptions because these things tend to go off from all these eruptions and go off in rapid frequency, they interact. And so we have to be able to reproduce a series of CVs.
And to use the flux storms for that. That's actually, because you have to put them to the code one after the other. How do you do that?
Well, typically it's a matter of adjusting parameters to reproduce the characteristics of each observed from mass ejection.
We built one of the things I covered is a tool that anyone can go online in the CCMC and design a flux or a model that they put in an active region. You can get almost immediate feedback with a zero-based simulation of what will happen if I put it with this, with these parameters.
But does it erupt immediately, or does it have to get into equilibrium?
Well, our whole goal is to allow people to build equilibrium conditions and slightly perturb. And I do think that's very important, but for some things, not necessarily everything.
And you can do more than one.
And you can do more than one.
Okay.
You find that.
Can I ask a question about that? So we decided to start toying around with putting CMEs in our model, which we haven't done yet. Would that be a good tool to help us initiate CME, or we just want to put a blob of density in some place?
No, well, everyone can have a very different thing to verify it. But the tool that we built is designed to use the local magnetic field of the active region as what's constraining what you put in. And it allows you to find an equilibrium, but the fluxor model we have, our laser model, is very flexible. You can almost build any configuration you want with it. I think that's very important because the initial phases of the eruption are very much determined by the forces in the active region. Unfortunately, at the same time, it's also very sensitive. So if you're just very much into an empirical modeling of local mass ejection, you can start with a big bomb, but then you can optimize very well and then get it to match something in the ionosphere. So it depends on the physics you're interested in. I'm very biased to that.
Similar, we have a tool established in CCMC called Equal, which you can run and would establish parameters for the Gibson structural producer eruption. Okay, that's contingent a bit upon our model and boundary conditions and things like that. So results may vary.
we're doing the study for a real CME event. Well, one way to do it from coconut, so from the corona, and then go all the way to Earth, or then only to inject it at 0.1 AU to see the effect. But our approach has become, especially for these very strong or very rare events that are harder to constrain with Icarus, because these Icarus simulations are computationally very cheap. What we usually do in this case is to do a bunch of simulations with Icarus because it's pretty cheap, so it's very easy to work with to constrain it better, especially for these rare events when it's very difficult to like just get to one constraint and then get everything right. But instead we have the freedom to play with it and see what's the effect with the Icarus simulations so fast.
Big experiments a little bit with Osprey, trying to combine multiple series for the mega event, and anything you can write down is a simple equation we can add in, but then you get into all sorts of decisions in terms of if you have two interacting, do they combine, do they bounce off one another, do they start reconnecting, that's gonna depend on orientation and things like that. But in theory, we should be able to come up with a decision tree, just implement that.
In Gamera, we're planning to include more than one CV, so which means that we will have multiple reasonable CVs going one after another, but this is a tedious work for the boundary conditions, especially for the magnetic field, so but it's a future work.
Something I think, Chip, you mentioned yesterday about shockwaves. For Whisper, we are thinking to have sequences of when we bring down the individual frames. We will not sum the images on board. So these are individual frames. So my question to you is, how big is the shockwave?
Okay, before you go answer, so we have 5 more minutes. We're going to cut off the line there, already standing up, and bear in mind we have 5 minutes.
Shockwave will collapse to the thickness of our punch grid. So hopefully we can get that down to maybe 164 for the solar radius in low corona. Yeah. Like region we could go potentially higher. I mean, it's a narrow region. We can make it as high as you want. It doesn't 2020, you know.
The big factor within the pixel and whether we can resolve it. So that's where we have to adjust also the exposure time. That's something
we should be able to match the grid resolution. We can certainly try to do that. Right.
All right, everyone's getting hangry, so either this will be short or I'll start a fight. Either one is good. I stood up because I got incensed when Bill said there will be observations with no CMEs. And that made me think about, you know, we have this riotous touring movie everyone keeps talking about, which is consistent with everything being ejected. There being no smooth thing, right? We're all used to the now venerable Moscow that has the smooth outflow and other stuff on top of it. All of you guys have refined in various ways. Are you ready for outflow that is completely discrete all the way down?
Yeah, they're ready.
Then it's turbulence.
Yeah, I mean, it was in the movie I showed. I'm ready and excited because I think that is getting closer to the physics of it.
We're working on our time models. So it's something we need to catch up on. We have limited capability, but are rapidly ramping it up.
We're also very, very excited with the Icarus, and also we are up farther. I think we're ready, and we have specific questions too if we can see them. And with Coconut, we just started doing that, so we start to see all these kind of outflows and dynamics going on. So also there we want to see if we can map or explain all these features that we.
We can show you today where we and one important issue is really looking into the details of how we do house the solution and trying to separate. So, yeah.
So yeah, following on from Lika's comment about how do we actually want to take this whole thing where we have new observations new models and solve the problems, like solve the coronal heating problem and the solar wind acceleration problem. The limitation I've seen so far is that the models that have coronal heating in them, Michigan and PSI and Delaware, are all based on different flavors of waves and turbulence. But there are other, if we want to solve the problem, we need to take all those things that the theorists have proposed and winnow them down. I mean, are there plans for including, interchange reconnection driven heating, all these other things that are out there, so that we can start to really rule things out? Maybe turbulence is the answer, and I'm a fan of it, but can we start to rule things out?
I haven't found anything yet that does not approximately obey on comment over a few. Approximately. Reconnection's fine.
Yeah, I mean, we want to increasingly improve our subgrid models, but if you're doing the global corona and the global Ionosphere, you have to make approximations, and that's the big challenge. How do I make the right approximations? Don't put it well, they're optimizing a very different way than we are, the Michigan is, and figuring that out is hard, but I think that's why it's good to have multiple modeling groups working on these things as opposed to one.
One of the things we have is, I believe it's unique as a multi-temperature model. So we also have the temperature anisotropies, the protons, and we can compare that to observations, which we're working on and have some limited success. Then we're really starting to delve into the limitations, or we know what's possible with getting kinetic physics information into an FHD model. So I think that's exciting avenue.
So as someone who swims in the code and numerics of these models, I think sometimes people believe the models are doing what they're doing too much. They just say, oh, this model does that, therefore it's true. I think that the numerical methods used in models, there's a lot of glitches, there's a lot of approximations, there's a lot of diffusivity, there's a lot of, if you're running something implicit at 10,000 or 100,000 CFL, are you really getting the physics in the way you want? Internally, it's hard to internally validate. These equations are very complex. There aren't analytic solutions for all of these things. But because of that, combined with the massive uncertainty of the boundary conditions, I don't think anyone should ever plot an in situ comparison with one line. I think you should always have a cloud of points around that spacecraft. That cloud may be extended to 5 degrees and to some kind of shaded uncertainty region. I know these models are too complicated to do multiple, like crazy amounts of ensembles of different boundary conditions and different, parameters in the model. But you have those layers. You have the uncertainty of the boundaries, of the boundary conditions. You have uncertainty of the model parameters. You have uncertainty of the numerics doing the physics you think the model's doing. And then the uncertainty that those physics are the physics. With all of that, there's no way you can compare 1 point to 1 point. So
So I'm seeing a lot of nods. We're going to need to wrap now. So I want to, and you guys can ask more questions outside of people, but we do need to stop for lunch. So let's thank our panel.